Okay, this is a typical free fall problem here. Before we do it, it's actually on the other side, but things to remember about all free fall problems. Okay, what do we know about all free fall problems that we can apply? Simon? Okay, little g. So let's say we have let's say we're using delta x equals VIT plus half AT squared. Say we need to use that for something. We are going to replace A with little g. Okay? So little g is equal to A is equal to negative 9.8. Okay, yeah. Delta x. We might replace that with delta y to tell us that we're working in the y direction. Anything else? What else can we say about any free fall situation? Other helpful tricks. Simon?
Acceleration's constant.
Okay, acceleration's constant. It's going to stay at negative 9.8. That is a big deal. Okay? So, let's say this. Something going up okay, that 9.8, that negative 9.8 still applies to something going up. Alright, now it makes sense when something's dropped or falling down. It's easy to see that negative 9.8, but that still applies when it's going up. Okay, what about the acceleration at the top? Okay, here's an easy question. What about the velocity at the top if I throw a ball up? Zero velocity at the top. Okay, what about the acceleration? Still negative 9.8 because gravity's still in total control. Okay, and this is going to be applied to projectiles too. Here's another thing that gets people. Okay, just some bullet points to help us out here. Let's talk about V final. We throw something up, it hits the ground. Okay, people want to go, oh, V final is 0 because it hit the ground and it stopped. Okay, now while that's kind of true, we always take V final to be the velocity right before it hits. Okay, V final is just that final velocity right before it strikes the ground. Okay, now what if VF is at the top? We already said that. Okay, we know that. We can apply that to a lot of situations. Okay, and that's basically it, guys. If we can remember these things and apply them to our equations, all of these problems work basically the same. Okay, so let's do an example problem. Alright, we already did the arrows and whatnot. This is a very typical free fall problem. Okay, so a person throws a ball upward in the air with an initial velocity of 15 meters per second. Calculate how high it goes. Okay, we got to calculate a bunch of different things here. Okay, so let's figure out how high this goes in the air. Here's an equation we like to go to for height. Delta y equals VIT plus half GT squared. Okay, anybody see any problems with that? Simon? We need time. Do we have time? We don't know time. Okay, good, Simone. We don't know time. All right, so we need to find an equation that doesn't have time in it. All right, so let's list what we know first. Okay, how high it goes. So we know this. We know that. Let's list our variables in blue. Okay, VI equals 15 positive, 15 meters per second. Acceleration is negative 9.8. Okay, and what else do we know? There's one hidden thing that we know here. If we're talking about the top of the path, Simone? VF equals 0. Good. Okay, V final is equal to 0. All right. There's another equation with height in it, okay, with this. We want to find a delta y. So we got this one, VF squared is equal to VI squared plus 2G delta y. And you could put A there, that would be fine. I put G in there to remind us it's little g. And we would like to solve for the delta y. So let's go ahead and rearrange that equation. All right, go ahead and do that. Rearrange it so it says delta y equals. We're going to want to subtract VI first. Okay, don't try and divide first. You got to subtract your VI squared. Now I'm going to divide 2G over to the other side. So I'll end up with delta y equals VF squared minus VI squared over 2G. All right, now we just need to plug in some numbers. Okay, so if you do that, your negatives are going to go away, which makes sense because this is going to be at a positive height. Okay, and so we get a delta y that is equal to about 11.5 meters positive. Let's box our answer. Okay, questions? Does that make sense? Okay, all right. You guys want a slang flashcard?
Yeah. I didn't
Busta. Okay, what possibly could this mean? Okay, a situation where you might see this used. Couple kids in a pillow fight. Take that, you pajama wearing busta. Yeah. Okay, now the definition. Let's check it out. Okay, there's the pronunciation. Person who attempts to be something he or she is not. Synonymous with poser, wanksta, scrub, and so on. Oh, second definition. A foolish, unsavvy individual who cannot hold his or her own. Okay, hope you learned something about that.
That's another use for the word busted. I have a question.
I don't take questions on the slang flashcard. Sorry, Simon. Okay, let's go on to the next one.
I don't get the answer.
Okay, how long is the ball in the air for? So now we want to find the total time of travel. Okay? And this isn't just to the maximum height. Okay, this is up and then back down. All right, so let's list what we know. VI is still equal to positive 15. Okay, I'm going to draw a little picture off to the side over here. Okay, the ball goes up, turns around, comes back down. Okay, so right here, the initial velocity, positive 15. Okay, velocity at the top is 0. What's the velocity when it comes right back down past the thrower's hand? Negative 15. Okay, that's something people forget as well. We know more about the velocities than we realize. Okay, so I'm going to go over here. I'm going to say my V final is equal to negative 15. And notice that it doesn't say that. It doesn't tell us that anywhere in the problem. We have to pull that out on our own. Acceleration still equal to negative 9.8.
Why do we use delta y instead of delta x?
Because we're working in the y direction. Delta x would be horizontal, so you just change it, and you wouldn't have, you get the same answer. Okay, Simon?
What's the, like, why do you need to call acceleration gravity?
Because if you want to leave it as a in the equation, you can. Putting little g in the equation just reminds you to use 9.8. Okay? All right, now there's one thing we also know here. We do know delta y. What is delta y? It's back where it started, so what's delta y? 0. Okay, now I don't need that for my equation because I'm just going to use VF equals VI plus AT. And that's going to get me the total hang time in the air. All right, so let's rearrange that. Do your subtracting first. Order of operations, okay, to get this how we want it, and then we'll divide by A. Okay, so let's plug in some numbers. V final is negative 15. So I have negative 15 minus a positive 15. All that divided by a negative 9.8. Again, you could put little g right there. Okay, so I have about negative 30 over negative 9.8. Okay, let's plug it into calculator. Negative 30. Okay. Divided by negative 9.8. Alright, I'm going to get about 3.06 seconds hang time in the air. Okay. So we'll leave that as 3 sig figs. Okay, now here's a common question that you can get asked here on these types of problems. How much time does it take for it to reach the maximum height? Do we need to do a lot of work here? Just divide it by 2. Okay? So we'll just divide that by 2 and we get 1.53. Okay, 3.06 to make the total path. Alright, it's going to take half that time to just get to the top. Okay, we don't really need to do a lot of work there. Alright, now part E, this is kind of a little bit of a challenge. At what time the ball passes a point 8 meters above the person's hand? Okay, now that is actually going to happen 2 times. Okay, what's my maximum height? 11.5. Alright, so right here, All right, 8 meters. So there's going to be 2 times where the ball is at 8 meters. Which equation describes, with respect to time, where something is at? Okay, this one right here. All right, so let's copy that down. Delta y equals VIT plus half AT squared. Okay, and let's just plug in what we know. So we know delta y is 8. Okay, from here to here, we know it's going to be a positive 8 meters. Our V initial is 15. We don't know time. Half of A, half of 9.8, half of negative 9.8. We get a negative 4.9. It's half of little g. And then we get a t squared. Okay, we haven't run into this yet. We've got a t and a t squared in the same equation. What are we going to have to do that your math teacher taught you? Starts with a Q. Quadratic equation. Now, do you guys want to know a secret way around the quadratic equation?
Yes.
It's secret, it's underground, it's like nobody knows. It's like the hipster method of finding t.
Foil.
Nope. Okay, first set the equation equal to 0. So I'm going to subtract the 8 to the other side. And I'm going to say 0 is equal to, and I'm going to rearrange how I write this a little bit. I'm going to put the squared first because that's traditionally how you do a quadratic. So negative 4.9 t squared plus 15t minus 8. Okay, now take out your handy graphing calculator. Okay, and we're going to plug this into our y equals and graph it. Okay, I already have it plugged in for us. Instead of t, you're going to have to use the x symbol. So negative 4.9 t squared is going to be x squared plus 15t minus 8. Okay, then I'm going to hit graph. I have my window preset ahead of time so it looks nice and pretty. All right, and here's how you're going to find out what time is. You need to find the roots of this. Okay, so in other words, where it crosses the time axis are going to be your 2 answers. So what you do is you hit second calculate, and you're going to calculate a 0 point. And it says left bound, right bound. So you can do this to move the little cursor around. So pick a point left of your 0, hit enter. Pick a point right of your 0, hit enter, and it'll say guess. I don't know why it says guess, but hit enter again. And that's your time. Okay? So T1, I'm going to call it, is at point, I'm going to round that to 0.69 seconds. We'll keep 2 past the decimal here. I know I'm not totally following the rules of sig figs here. Okay, 0.69 there. Alright, now hit enter again, and let's get the other one. Second calculate 0. Here left bound, enter. Right bound, enter. Sure, guess. Okay, and we get 2.37 for our second time. So I'll keep 2 past the decimal. T2 is equal to 2.37. Alright, now let's make sure this all makes sense. We've got 4 times on our page here. Time to go to the top is 1.53. So the 0.69 happens sometime before that. Okay, so that's good. All right, then we pass through a time of 2.37 right here, and a total time back to the bottom of 3.06. So our timeline kind of makes sense. It's chronological. Everything is happening as it should. All right, so this is a very typical free fall problem. You might encounter something like this on UT, something like that. Okay, so hopefully that's a good example for you guys.